Welcome to this web lecture about external cognition, about extending our cognitive abilities by using external tools or even other people. We talk about external cognition when we interact with external representations of information. We may have maps to guide us through a physical space. We may use notes and diagrams to make sense, right, of otherwise abstract information. The cognitive benefits and the processes involved will be studied, and the benefits will of course be clear. We can just do more, right, when we don't rely on just our own brain. We will see how it works to extend our cognition and what computer-based representations we can use to develop and to help our brain even more. First part is to externalize information to reduce the use of our memory. We cannot remember everything. So if we can use a tool to take away some of that load, we can concentrate on other tasks at hand. A diary and reminders and calendars are very important to not keep us occupied during the day with thinking about what comes after this meeting. And if you have to keep track in your mind of everything you still have to do, right, it takes away your attention of actually doing the tasks. So calendars are very important. When we go to a shop, we want to use shopping lists so that we don't have to remember what is different in our shopping today than it was yesterday or the day before. Right? And we need to-do lists for tasks. They are all written either on paper or they're written in a computer to remind us of things that need to be done. Some at a specific time, others at any time or in a certain prioritized way. So the task list, for instance, is typically not timed but has priorities. And other lists indicate when to do something. We can also help our brain in sort of summarizing or keeping track of a large amount of information, right, by means of annotation and tracing. Annotation means that we modify the existing representation through certain marks. A typical way in which mostly women, more than men, annotate documents is by using a yellow magic marker to highlight important phrases. When we go to a supermarket and we have our shopping list, we will cross off the items we already have in our shopping cart. Just because it's easier to not have to check in the shopping cart what's already there each time, right, after we added something and we have to look for the next item. Underlining, right, also where it's ticking off. Sometimes we also want to develop cognitive traces, right, by manipulating items so that they make sense for us. This is done, for instance, when we play cards. A lot of people, right, they get typically 13 random cards, and if you're a good card player, you will take these cards and you will just hold them in your hand and that's it. The lesser players need to actually place them in a certain order. Spades together, clubs together, which of course gives clues to the other players. You should never do this, right? Yet we tend to structure the information so that it's easier for ourselves, right, to make sense of it. We also use computational offloading to use a tool and external representations to work with numbers. Pen and paper is already an example of that. It doesn't have to be a calculator. But the representation is more important than you often think. Let's try to compute this. I probably don't have to wait a long time because you're not going to be able to do this. You're not able to do this unless you translate it to 234 times 456. Well, it already said so, right? But we haven't learned how to compute with numbers in Roman representation. Even not a simplified notation, as you notice that I used 4 I's instead of IV. Can't do it. Right? We have learned to work with a specific external representation using the digits, right, in a 10-digit form. Otherwise, we cannot do the computation. Problem solving, planning, deciding, decision-making is a more complex area, which involves what we call reflective cognition. We have to think about what to do. We have to consider our different options and consequences and try to find an optimal solution. Now, this thinking, discussing with others, and using artifacts will help us do that. We can create mind maps, as we will see. We can take notes and use books and pen and paper. Brainstorming is a good example of the use of tools to support that. They can be a whiteboard, they can be a flip over, but when you are discussing and already using each other's minds, right, to solve the problem and like do brainstorming about the new interface design, right, you will use these external tools to structure the thoughts. A design implication is that we need such a tool for visualizing our reasoning. Nowadays, mind maps are frequently used for this. And you can write down ideas and connect them with different types of lines, right, to say this implies this other, or this idea contradicts that other. And there's been research on automating this process to actually have systems recognize which of the ideas imply which others, right, so that it helps the decision-making process, that if you have taken a decision on some aspects, it shows you the consequences rather than you having to come up with them yourself. Information visualization is another way to use tools to make sense of large amounts of information. Right? The mind map helps to structure your thoughts, but that's small bits. Right? Visualization tools are typically used for masses of data. What you should do, right, besides this lecture, is you should look up Sequoia View, a tool developed by Jack van Wyk from our university that helps you answer the question, why is my hard disk full? It structures a presentation of what is on your hard disk in such a way that you immediately see where the space gobblers are and what you need to delete to free up a lot of space on your hard disk. Then there is the distributed cognition, where different individuals are going to work together to solve problems. Together with each other, and perhaps also with external representations with computerized tools. The information is transformed from what you are thinking into media, which is then given to the other users. So we cannot yet directly connect our brains. We will use a transformation from ideas, perhaps to language, right? And then the other person interprets the language and transforms it to ideas, and hopefully we will both end up with the same idea. The transfer can happen through computer displays, to sound, to paper, right? Unfortunately not directly from head to head. So information processing, typically it happens in our own brain. That's what we see on the left, right, where we are connecting different ideas and inputs and outputs. And now we have to transform that into a similar thought process where different brains are involved. Different brains solve different parts of the problem. What is involved there? It is distributed problem solving. And a good example of that is flying an airplane. And what is special about flying an airplane, apart from the general problem area, is that typically the pilot and the co-pilot or first officer, they actually can both fly the plane in the sense that they can both do everything that's involved. In the previous example of distributed processing, not everyone needs to have the same capabilities. When flying a plane, typically they do. So what's involved is they have redundant controls also, but they have to communicate about who is going to do what and who is going to react to which event that happens. They have verbal and they have non-verbal communication. Something goes wrong, where they will look at each other, right, and also take up visual, non-verbal signs. They need to have coordination mechanisms, perhaps through rules or procedures. Like when you land the plane, you have to do a lot of actions at the same time. Right? Who is going to do what? Who holds the steering wheel? Who is going to control the throttle? Right? Who is going to activate lowering the landing gear? Right? It has to be coordinated. Both people can do it, right? But they have to decide who does what. Right? That's what the procedures help for. They have to communicate. They have to tell each other what they do. Right? They can't all the time look at each other or look at what the other person is doing, so they will also communicate through language. And in the end, they will share knowledge. In the end, both need to know, right, what is going on at any point in time. Now, that is not always true in collaboration in general. You are going to work in groups on an assignment. Like the final assignment is to design and build and test a prototype for a room thermostat. Not each student in the group has the same prior knowledge, has the same skills. So you are going to divide up tasks, and you are going to share knowledge, but it doesn't have to be complete knowledge. Not everyone in the group will know every detail of the design or every detail of the implementation. So crucial in this distributed cognition is that in the end, the combined brains can perform the task. And unlike with flying a plane, right, each individual brain does not need to know everything. That's what makes collaboration an interesting problem area, and how to essentially minimize the amount of communication and coordination that is needed to produce a successful result in the end. I wish you a lot of success with the final project in coordinating your work so that the brains combined, right, can actually produce a much better result than each of you could have done individually. Thank you for participating.